Okay, so hi everybody. So today we're going to go ahead and start on 4.4 notes, which is coordinates and basis. Sorry about that. Okay, so let's just jump right into it. This is a pretty important topic, and I think one that's a little bit difficult to understand at times. So we'll try and go a little bit slowly here. Okay, so anyway, what is the basis? If V is any vector space and S is a set V1 through Vn, a finite set of vectors in V, then S is called the basis for V if the following two conditions hold. Okay, so the first one is that S is a linearly independent set. Okay, so we have to make sure that's linearly independent. Okay, so B is going to be that the span of S is equal to V. Okay, we just need to make sure that the S spans V. Okay, now we'll come back to this in a minute because there's actually a really important reasons why this is so. Okay, but on a side note, okay, so notes. The basis is like creating a whole new set of coordinates. Okay, so the basis is like creating a new coordinate system. And this is a system where the directions of the basis vectors establishes the positive directions. Okay, and its lengths of the basis vectors establish the spacing between the integer points on the axes. Okay, so that's what a basis is. Okay, so now what exactly does it mean? So first, think about the vectors I, j, and k. Okay, so if you have the vectors I, j, and k, hopefully you can see that is going to, according to this, they're linearly independent. It's going to span, and we're talking about R3. It's going to span R3. So hopefully you can see that this is going to be a basis for R3. Now, IJK is, if I actually drew these in, this would be I, J, and K. And of course, you could switch this depending on how you want to orientate it. But this is going to give the positive direction, and positive direction, just like we'd normally know. Okay. Now, the length, I, J, and K are unit vectors, which means it has a length of 1. Now, you have to be careful what you mean by 1 here. Like, 1 what? Okay, 1 meter, 1 yard, 1 foot, like whatever it is. 1 is kind of a relative term here when we're talking about quantities 1. Okay, what exactly does 1 mean? Okay, so anyway, so the unit vector, so it means the length of 1 is the distance from there to there. So this establishes what 1 is, what 2 is, what 3 is, and so on. Okay, now why are these two important? Linear independence and the span of V. So if you think about this, what we're trying to do is we're actually trying to recreate a system. So say we're in R3 and we want to come up with some set of vectors that's going to span all of R3. When doing so, in R3, there's an infinite amount of different points there, and each point can be represented as a vector. Now, if the set S spans R3, then that means every single point in that space, so everywhere it could be, can be represented as a linear combination of I, J, K, or the vectors in that set. Okay, so that's what it means to be spanned. Every number in that space can be represented. Now, why is it important to be linearly independent? So the reason why it's important to be linearly independent is because if we don't establish that fact, sure, we can span R3 all day long, but if we don't make sure that they're linearly independent, then there's a chance for redundancy, to be able to represent one point in a multitude of ways, or a positive and a negative direction at the same time. Okay, so we have to establish both these things in order to move forward. Okay, so let's do a couple examples. Okay, so show that this is the basis for the vector space P of n, the polynomial of degree n or less. So this is a set of all polynomials of degree n or less. So I have to show linearly that it's linearly independent. And I also have to show that the span of x of 1, x squared, all the way up to xn is equal to P of n. Okay, that's what I need to show. Okay, so how do I show these? And notice I didn't give you a whole lot of room here. And the reason why is because we've actually already done this. If you go back and you look at example of 4.3.4, we actually showed that the set is linearly independent. And then we also showed in example 4.2.7 that this set S spans P of n. Okay, so these tell us that the set 1x all the way up to xn is a basis for Pn. Okay, so pretty simple. Okay, example 4.4.2. I want to show that these vectors form a basis in R3. And this should not be there. I apologize, I meant to take that off, but I forgot to. Okay, so what I'm trying to do is I need to first show that they're linearly independent. Okay, which means I'm going to take C1 V1 plus C2 V2 plus C3 V3. I'm going to set it equal to 0, and I'm going to show that the only way that this possibly works is by the trivial solution where C1, C2, C3 is equal to 0. So plug in the vectors. So C1 times 1, 2, 1 plus C2 times 2, 9, 0 plus C3 times 3, 3, 4, and that's going to be equal to 0. Okay, setting up the system of equations. So C1 plus 2C2 plus 3C3. So C1 plus 2C2 plus 3C3 is going to be equal to 0 because that's the 0 vector. Furthermore, I have 2C1 plus 9C2 plus 3C3, that will also be equal to 0. And then I also have C1 plus 0, because that times 0 is 0, and plus 4C3 is going to be equal to 0. So we know, we've been doing this for a little bit of time now, we know what I need to do is I need to figure out what the determinant of the coefficient matrix is. Just take all the coefficients over here. So I have 1, 2, 3, 2, 9, 3, 1, 0, 4, and I have to figure out what the determinant of this is. So what I'm going to do is I'm going to go ahead and I'm going to take the determinant along the bottom row, okay? Because I'm going to pick the bottom row because you have a 0 there. So I'm going to take 1, so this column, this row goes away, and I just have this determinant. By the way, do you have to pay attention to the plus minus part? So plus minus plus minus plus minus plus. So I have 1 times 6 minus 27. Okay, minus 0, so I don't need to worry about the 0 because 0 is going to go away, plus 4 times 9 minus 4, which gives you 5. So this is equal to negative 21 plus 20, which is equal to negative 1, which is not equal to 0, and that's the important part there. Now, at this point in time, we have to interpret exactly what this means. So I guess I would advise you to pause the video for a moment and go ahead and try and remember what that does mean. Okay? So what does that mean? So if we have a determinant that's not equal to 0, that means that the matrix is invertible. Okay, so if you go back to the system of congruency statements, we had that A is invertible for the homogeneous system of equations. So if A is invertible, then you know that the only solution there is the trivial solution. Okay, so this means the only solution is the trivial solution. And this, of course, is for a homogeneous system or homogeneous system of equation. Homogeneous means it's all equal to 0. Okay, now because it only has a trivial solution, that means that the set V1, V2, V3 is linearly independent. Okay. Okay, then I have to show that it spans it. So I want to show, to show the span of V1, V2, V3 is equal to R3. Okay, show it's equal to 3 space. Okay, so how do I do this? So spanning means every single point that's in that 3 space can be represented as a linear combination of V1, V2, V3. So I'm going to let B, we're going to let B, which is equal to B1, B2, B3, be an arbitrary vector in R3. So what I know then is I know I'm going to take C1 V1 plus C2 V2 plus C3 V3, and now I want it to be equal to B. So in other words, when I actually write it out and I split it apart, it was a system of equations, it's going to essentially be this system up here, but instead of 0, 0, 0, it's going to be B1, B2, B3. So I have C1 plus 2C2 plus 3C3 is equal to B1. I know 2C1 plus 9C2 plus 3C3 is equal to B2. And I have C1 plus 4C3 is equal to B3. Okay, so all I have to do is solve this system. Now I know if I write this as a matrix equation, that the coefficient matrix is going to be invertible, which means for every vector I choose B, B1, B2, B3, can be any vector at all. Since the coefficient matrix is invertible, that means I'm able to solve that system, which means it doesn't matter what B1, B2, B3 I pick, I can find a set of C's that will make it work. Okay, so therefore, because the determinants of, I'll call it A, I guess, is equal to -1, which is not equal to 0, then A is invertible. And this thing right here is going to be equal to A. That's the thing that's equal to A, which implies that the span of V1, V2, V3 is equal to R3. Okay, which means that the set V1, V2, V3 is a basis for R3. Okay, which means I can take any linear combination of those and map exactly to 3 space. Okay, next example. So now we're going to be dealing with matrices. Okay, that's a little bit more difficult exactly how this looks, but I think we can go with it here. Okay, so I show that these set of matrices form a basis for the vector space M22. So same thing I have to do again. I have to take C1M1 plus C2M2 plus C3M3 plus C4M4 and set equals 0. That sure was rhythmic, wasn't it? Okay, so in doing so, I'm going to have, and hopefully you can see this. So if I'm going to take C1 times M1, I'm going to multiply it in here. It's going to be C1 and everything else is going to be zeros. When I pay C2 times M2, that's going to become C2, but everything else is going to become zeros. So when I reduce this, this is going to give me C1, C2, C3, C4 is equal to 0, 0, 0, 0, because that is the 0 matrix. Okay, so what does that imply? That implies C1 is equal to C2 is equal to C3 is equal to C4, which is equal to 0. So what do I know? The set M1, M2, M3, M4 is linearly independent. Okay, that's what I know. Okay, furthermore, so I have to show the span now. Okay, so the span is essentially the same thing. C1, M1 plus C2, M2 plus C3, M3 plus C4, M4 is equal to some vector B. Not vector B, matrix B. A 2 by 2 matrix for B is equal to B1, B2, B3, and B4. Okay, so this, once again, reduces to this. So I have C1, C2, C3, C4 is equal to B1, B2, B3, and B4. Okay, what does that mean? That means regardless of what vector, or sorry, a 2 by 2 matrix I choose. So these numbers can be anything. All I have to do is choose the coefficients be C1, C2, C3, and C4, or to be those, and that's it. It spans it. Okay, so therefore, the span of M1, M2, M3, M4 is equal to M22. So therefore, the set M1, M2, M3, M4 is a basis for M22. Okay, I was just able to express it in a different manner. Okay, example 4.4.4. Okay, it should show that the vector space P of infinity of all polynomials with real coefficient has no finite spanning set. Okay, so we're going to let S be a finite spanning set. So let S be a finite spanning set where S is equal to P1, P2, all the way up to P. R. Okay. Where the maximum, and there has to be a maximum because it's a finite set, where the maximum degree is n. Okay, so the largest polynomial I can make in there is going to be n. Okay, well, this means there is no linear combination of P1, P2, all to Pn that will make a polynomial of degree n plus 1. Okay, so it doesn't. So it kind of cannot span that. Okay, so we have a special name for these. So note, a vector space that cannot be spanned by a finite number of vectors is said to be infinite dimensional. Okay. If it can, then it's called finite dimensional. Okay. Otherwise, it is said to be finite dimensional. Okay, so what are some examples of finite dimensional? Okay, we know Rn, we know Pn, and Mn Mn are finite dimensional. Okay, on the other, and I'm just going to basically make this claim. You actually have to do one of these in your homework. But I'm going to make the claim that R infinity, f from negative infinity to infinity, so it's a set of all functions defined on the interval. C from negative infinity to infinity, it's a set of all continuous functions on that interval. Cm from negative infinity to infinity, so that's m times differentiable or continuous on the interval from negative infinity to infinity. And C infinity from negative infinity to infinity are infinite dimensional. Okay, next page. Okay, uniqueness. Now, are these vectors unique? So if I'm given a basis, one basis, is it possible that I take any arbitrary vector in that space and I'm able to represent it in two different ways? And the answer is no here. Okay, so if S is the set of vectors v1 through vn is a basis for the vector space V, then every vector in V can be expressed in the form here. That should be a lowercase c. I'm not sure why that's an uppercase c. Sorry about that. In exactly one way. So how do we do this? We do this by proof by contradiction. Okay, so since S spans V, it follows that every vector in V can be expressed as a linear combination of vectors in S. Okay, so we're going to assume that there's more than one. Okay, so assume that there is more than one way to represent V. Okay, so I have V is equal to C1 V1 plus C2 V2 plus all the way up to Cn Vn. But at the same standpoint, I can also represent, I'm assuming that I can to lead to my contradiction, V is equal to K1 V1 plus K2 V2 plus all the way up to Kn Vn. Okay, I can represent those two exactly different ways. Okay, now I'm going to subtract the two equations. So I take V minus V and I get 0. So subtracting the two. I get 0 is equal to C1 V1 minus K1 V1, factor out the V1, and you have a C1 minus K1 V1 plus C2 minus K2 V2, and then all the way up to Cn minus Kn Vn, and that should be equal to 0. Now, what do we know about the right-hand side here? The right-hand side is just a linear combination of the vectors in S. So therefore, it is linearly independent, okay? Which means that each one of the coefficients should be equal to 0. So C1 minus K1 is equal to 0, C2 minus K2 is equal to 0, and so on, all the way to Cn minus Kn is equal to 0. And that implies C1 is equal to K1, C2 is equal to K2, all the way up to Cn is equal to Kn. So what does that mean? The C's and the K's are the same. So this isn't actually a different way of representing that vector V. It's exactly the same way. Okay. This implies that the two representations of V are the same. Okay, so it is unique. Okay, definition 4.4.2. So if S is a set of vectors v1, v2, all up to vn is a basis for a vector space V, and V is equal to C1 V1 plus C2 V2 plus all the way up to Cn Vn is expressible is the expression for a vector V in terms of the basis S, then the scalars C1, C2, all up to Cn are called the coordinates of V relative to the basis S. Okay. Oh boy, it was way off. Sorry about that, you guys. Just kind of talking. Let me read through that again then. Okay, so if S is a set of vectors v1 through vn is a basis for a vector space V, and V is equal to C1 V1 plus all the way up to Cn Vn, and is the expression for vector V in terms of the basis S, then the scalars C1 through Cn are called the coordinates of V relative to the basis S. Okay. Let me write out the rest of this then. Sorry. The vector C1 through Cn in Rn is constructed from these coordinates is called the coordinate vector of V relative to S. And we denote this as V of S, which is equal to C1, C2, all the way up to Cn. Okay, so just a couple more examples and then we're done with this section. Okay, example 4.4.5. Okay, so we have, in the special case, where V is equal to Rn and S is the standard. That means each vector there has a unit length of 1. As the standard basis, the coordinate vector V of S and the vector V are the same. So V is equal to VS. Okay. So for example, I know this is like a sub-example, right? So example, so say for example, you have the set of vectors V1, V2, V3 that are equal to, nope, that's wrong example. Sorry. A vector in R3, which we know is going to be equal to V is equal to A, B, C, can be written as A, V is equal to AI plus BJ plus CK. And that's that. Okay, just rewriting it like that. Okay, so it happens to be in the same space. Okay, so the last one, we have these vectors 1, 2, 1, 2, 9, 0, 3, 3, 4. We've actually seen these before. Be a basis for vector R3. Find the coordinates of that thing. Okay, so what do I know? I'm going to take the coordinate. Okay, so this right here is just a vector in R3. Okay, that's all it is. So I'm going to take that vector and I'm going to rewrite it as a linear combination of the rest of them. So this is C1 times 1, 2, 1, plus C2 times 2, 9, 0, plus C3 times 3, 3, 4. Okay, and then rewriting the system, I have C1 plus 2C2 plus 3C3 is equal to 5. And I have 2C1 plus 9C2 plus 3C3 is equal to negative 1. And you have C1 plus 4C3 is equal to 9. Okay, so that is a system we've had before. We know if we take the determinant of the coefficient matrix equal to negative 1, so it is invertible. And if you happen to solve it, which I'm going to let you do, so MATLAB, Gauss-Jordan elimination, reduced or echelon form, augmented matrix, whatever you want to do, it turns out that C1 is equal to 1, C2 is equal to negative 1, and C3 is equal to 2. So therefore, what I have is I have V of S is equal to 1, negative 1, 2. Okay, so what does that mean? Like, interpret that. What exactly does it mean? Okay, what that means is this point, 5, negative 1, 9, which is the typical standard normal vectors that we used to. So that represents some point in space. Okay, now if I take that point in space and I change the coordinate system, instead of I and J and then K, and if I change the axes to be V1, V2, V3, so this set right here, then this point we no longer call 5, negative 1, 9. We now call this point 1, negative 1, 2. Now it's important to understand that this is exactly the same location in space, exactly the same location. It's just based off of a different coordinate system. That's all it is. Okay? Okay, so that's all we got for 4.4. Hopefully you guys understood that. I know it's quite complicated. So all the best of luck, and we'll see you in 4.5.